This is Unit 4, Atomic Structure, Part 1 Notes. By the end of this unit, you should be able to understand the modern atomic theory in regards to their experimental designs and conclusions, as well as identify the number of protons, neutrons, and electrons in neutral elements and ions. You should also be able to differentiate between what a cation is and an anion. So these are some of the scientists that you should be responsible for in understanding what they did experimental-wise and how they changed the structure of the atom throughout the years. The first one that you should look at is Dalton. Dalton, he discovered that all elements are made of tiny, indivisible atoms or particles that are known as atoms. So he just knew something was there. So his depiction of the atom was just a big sphere of just stuff. It was just a dense sphere full of little tiny things called atoms. Thomson came in later on and he did this experiment known as the cathode ray tube, which will be on the next slide. And what he did was that he discovered the electron. That's the particle with a negative charge. And he did the cathode experiment, which led to the plum pudding model. So he changed what the atom looked like by, instead of just saying it was a sphere, okay, so he agreed that it was circular, but it was just full of a whole bunch of positive area, and in the middle there was these little electrons. So it kind of looked like a chocolate chip cookie, but back in the day, their chocolate chip cookie was known as plum pudding, so he came up with this plum pudding model to show that you had a positive dense area and then just little electrons spaced out in between that. So that was Thomson. Later on, Rutherford came in and he did an experiment using gold foil, and he shot something known as alpha particles. Those are positively charged particles through the nucleus or through gold foil, and he actually changed the structure of the atom very dramatically to where instead of having a whole bunch of positive all over the sphere like Thomson did, he determined that the positive area of the nucleus was actually really small, it was really dense, and everything else was full of empty space. So he dramatically decreased the size of what is known as the nucleus. Then Bohr came in, and instead of just saying all the electrons were everywhere around that small nucleus, he localized them into energy levels. So that's where you see the little lines going around in circles. The electrons are on the energy levels, and they orbit constantly. So he was saying that the electrons are at a fixed position around the nucleus, but they are orbiting around and around and around, just like the planets orbit around the sun. And then Schrödinger, he dramatically changed the position and the velocity of electrons by using quantum mechanical mathematical equations. So that goes into a whole bunch of physics aspects of experimentation, but he pretty much determined that the likelihood of finding an electron within the electron cloud. So based on where the electron is and how close it is to the nucleus, we could find the position of electrons later on. But the four most important scientists that you should be responsible for will be Dalton, Thomson, Rutherford, and Bohr. So more specifically, Dalton identified 4 postulates, and this was after he determined that his atomic structure was just a big sphere of dense stuff. There's really no technical terms for what he called it, but his idea of the atom just looked like a big sphere. But he determined that all elements are made of tiny, indivisible particles known as atoms, and that atoms of the same element are identical. So all carbons are carbon, all nitrogens are nitrogen, and all sodiums are all sodiums. They're similar. There's no difference between different or multiple atoms of the same element. And he also determined that atoms of different elements can physically or chemically mix together, meaning that if you have atoms or different atoms together, you can physically mix them. And going back to our Unit 3 stuff, physically mixing atoms or substances together, you get mixtures. Or you can chemically combine elements to make compounds in fixed ratios. And then he also determined that chemical reactions occur when atoms are separated from each other, joined, or rearranged in a different combination. So you are changing the compound at the end. And any reaction is a chemical reaction, so you're changing what the substance is composed of at the end. So then, once Thomson came in, he took that sphere that Dalton made, and he told us that, hey, there's probably different parts of positive and negative areas. So what he did is the cathode ray experiment, where he shot different electrons or electricity, which is electrons, through this cathode ray, if you look at the very bottom, and you see that line going straight across, that's just a stream of electrons. And he used magnets on either side, and you can look at this line here, and it's going towards the top of that little tube. So we should know that electrons have a negative charge, so what he is actually holding, he is holding a positively charged magnet, because we know negative is attracted to the positive. And he also held a negative magnet towards the bottom, and that also shot the ray of electrons towards that positive side. So he founded the electron because he knew something was attracted to the positive side, hence electrons are negative. So what he ultimately did was say that that dense area was full of negative charge, and that you had little areas of negativity, so the blue would be the electrons, around there. It looks like a chocolate chip, but they call it the plum pudding model. And that was Thomson. So then after Thomson, we had Rutherford, and he used alpha particles. Alpha particles are just positively charged they're positively charged atoms, and he shot them through. Here's this piece of gold foil over here. Shot it through. And what he did was that he took Thomson's idea of the atom, and then he had a whole bunch of negative side. Well, what he did was he discovered that most of the alpha particles went straight through, and only very few particles deflected back. So most everything went straight through the gold foil. So what he did was he took the nucleus of the atom, because we know that alpha particles are positively charged, they went straight through, and whenever they hit a small, dense center, he knew that the center of the nucleus had been positive, but it was actually really small. So Rutherford ultimately decreased the size of the nucleus, and he called it a small, dense center, and most everything else around the nucleus out here, that is just where your electron cloud is. So overall, there's 3 different particles that make up an atom, known as electrons, protons, and neutrons. Electrons are negatively charged, and they have the symbol E to the negative sign, and they have ultimately a -1 charge. And their mass is 9.11 times 10 to the negative 28th, and the electrons are the only part of the atom that's located outside the nucleus. Protons are positive. They have a symbol with a little p with a plus sign. They have a +1 charge, and they have a mass of 1.67 times 10 to the negative 24th. And they are also part of the nucleus. So if you look at this, neutrons and protons both make up the nucleus, and that is the smallest dense center located at the center of the atom. Neutrons are neutral. They do not have a charge at all, but they do have some sort of mass. And if you look at the mass values for protons and neutrons, they're the same. And compare that to the exponent of the electron. The electron is 4 times smaller than a proton or neutron, hence it is considered ideally massless. So electrons do not contribute to any of the mass or the size of the atom. They only allow for the electron cloud and where they are spaced around the nucleus. So the biggest things that we need to understand from this slide here is the 3 particles, 1, 2, and 3. Electrons are negatively charged, protons are positively charged, and then neutrons, these are neutral. The mass values are not necessarily that important, but you need to know that electrons are considered massless, and only protons and neutrons contribute to the overall mass of your atom. To analyze elements in a periodic table, we have to look at a couple of things. The first one is the top value. For example, in carbon, that's 6. That represents the atomic number. That is the number of protons in your atom. And protons identify, or the atomic number identifies your element. If you change the proton number, you're changing the element in general. So protons will lead you straight to the element that you're talking about. The C represents the symbol, carbon, that represents the chemical name, and the number at the bottom, that is your atomic mass. Mass is the addition of all the protons and the neutrons in an element. And there's an easy way to remember how to calculate or identify some of these materials or particles. If you just remember ape man. So the atomic number is equal to the proton number and electron number, and that's only for a neutral element. So in a neutral element, the protons will equal the electrons. So again, that's your atomic number is equal to the protons, which is also equal to the electrons. So I can write that out. Proton number and electron number, and that's only for a neutral element. And then the man portion of it is just your mass number minus the atomic number is equal to your neutrons. So we have mass, or your atomic mass, minus atomic number, which is also known as your proton number, is going to be equal to your neutron number. So if you know the mass and you know the atomic number, you take the 12 here minus the 6 for the atomic number, and that leaves you to have 6 neutrons in carbon. Okay, so practicing just a little bit on identifying the different parameters of the following elements. The first one, we have sodium. If you look at the symbol over here, we have atomic number, which is 11, because that is the top number. And if you remember our ape man, the atomic number should equal the proton number, which should also equal the electron number if it is neutral. Okay, if it's not neutral, there's going to be a charge in the upper right-hand corner, but there's nothing there right now, so we are assuming everything we have here is neutral. So if our atomic number is 11, our protons are 11, and then we have 11 electrons. Okay, and then our mass number is at the very bottom. It is 22.99, just I'm rounding to the 2 numbers past the decimal point. And then how do we calculate neutrons? That is just the mass number minus the atomic number. That'll equal our neutron number. So that's your ape man. I have my mass is 22.99 minus 11. That is our atomic number, or the proton number, and that equals a total of 11.99 neutrons, otherwise known as 12. Eventually we'll be able to round these numbers, but for right now, let's just extend out to 2 decimal points. And then looking at the next example, we have fluorine. That's the symbol F. The atomic number is in the upper or the top side of this picture here. So the atomic number is 9. For a neutral element, the protons equals the electrons. Just to review that real quick, if protons are positive, electrons are negative. If we total up 9, positive 9 and a negative 9, it equals 0. Hence, that's a neutral element. Then our mass number down here at the bottom is 19.00. So how many neutrons do we have? Well, following the ape man, the mass number minus the atomic number will give us 10 different neutrons. Okay, so before, when we used the ape man, that was when the atomic number is equal to the proton number, which is equal to the electron number if it is neutral. But now we're going to introduce something known as ions, where they differ from straight neutral elements. A neutral element is where the proton number equals the electron number. But for ions, those are your charged atoms where the electron number differs from the proton number. So for any element, the proton number will never change. So if we look at sodium, if you look on the periodic table, the atomic number for sodium is 11. However, there's a different amount of electrons because of this upper right-hand charge. So if we add the protons plus the electrons, that's going to equal our charge. Okay? So if our protons are positive, I need to add in the amount of electrons to total up to a +1 charge. That's because there's a +1 on the upper right-hand corner of sodium. So if I have 11 positive, and if I add a -10 here, that will leave me to an overall +1 charge. So hence, sodium only has 10 electrons. Looking at oxygen, that atomic number is 8. I have 2 more electrons to give me an overall -2 charge, because a -10 plus a +8 will overall add up to that -2. Then for magnesium, magnesium has an atomic number of 12. It has a 2 plus, meaning there are less electrons, because a +10 plus a +12 plus a -10 leads me to an overall +2 charge. And then for nitrogen, the atomic number is 7, looking on the periodic table. That's where I'm getting those values from. And it has a -3 charge, meaning it has 3 more electrons, because a -10 plus a +7 equals an overall -3. So adding the protons and the electron number should lead you to the total charge of your ion. That comes into play where we're identifying cations and anions. Cation is defined as where the electron number is less than the proton number, meaning there's an overall positive charge. So anytime you see a positively charged ion, such as sodium +1 or magnesium +2, those are your cations. Anions have more electrons than protons, so they have an overall negative charge. So your oxygen with a -2 charge and your nitrogen with a -3 charge are both your anions. And if you can remember this, the T in your cation looks like a positive charge, and that's how I remember that cations are always positive, and then your anions are always negative. Okay, so now you're going to practice identifying the proton number and electron number for these different elements or ions. So sulfur has an atomic number of 16, because that is what is located on the periodic table, and it has a -2 charge. So the overall charge should equal -2. So if protons are positive and electrons are negative, if I were to add only 18 electrons, a +16 plus a -18 will equal an overall -2 charge. So then potassium, there is no charge in the upper right-hand corner, so you're going to assume it is neutral. Okay, so the atomic number for potassium is 19. If it is neutral, the protons should equal the electrons. Then we have boron, has an atomic number of 5, and it has a +3 charge. That means it has less electrons. So if I add a +5, and then I have a -2, that would equal an overall charge of +3. So that is why boron has 3 less electrons. And then fluorine has a proton number of 9, because that is the atomic number. There's no charge in the upper right-hand corner, so again, it's neutral. If it is neutral, you need the same amount of electrons and protons, because a +9 plus a -9 will cancel out to being 0. Just like in potassium, a +19 plus a -19 equals neutral or 0. And just to review real quickly, to get the neutron numbers, you would take the mass number, the atomic mass of each of those elements, minus the atomic number, also known as your proton number, and that would give you the neutrons. So overall, you should be able to identify protons, electrons, neutrons, atomic number, and atomic mass for all of these elements. Okay, so have you accomplished the objectives of this unit, being able to identify the modern atomic theory and how the structure of the atom changed over time? Are you able to identify protons, neutrons, and electrons for neutral elements and ions? And are you able to tell the difference between a cation and anion? Don't forget, the T in cation looks like a plus sign, so that's why positive ions are cations, and then that means your negatively charged ions are known as anions. Okay, and if you are confused or you have questions, please write them down or highlight the areas of your notes that you need to ask questions over, and we will look at those and answer those questions the next time that I see you in class.